My name's Justin Grass, and this is my MIS 4460 final project. So the problem we have at work is we want to forecast markets with little to no data, specifically these self-driving taxis. We want to know how large this market will be, how many vehicles will there be, how many will need to be built, and how long will they last. And so the solution is for us to conduct our own research, go out and find data that we think is relevant and make our own estimates. This market currently doesn't exist, and it's kind of completely speculative. There are no self-driving, commercially available taxis for you to hail today. And here's a snapshot of what my dashboard will look like. So how this model was developed was I took New York City data. I figured that the current taxi market is a good proxy estimate of the future taxi market. And once I had an idea of how the New York City taxi market operates, I looked to census data and I started to apply the New York City analysis to the 50 largest cities in the United States. And I've given this presentation, or a version of this presentation, to many people at work, many other students for other classes, and I've written papers about this for other classes. And I've gotten a lot of feedback, and I've combined all these three things into what I'm calling this model for the L4 taxi market evolution, with L4 taxi being self-driving taxis. And so how does this model work? We have two variables, the market limit and the mean life. The market limit being how many vehicles are in the market currently today, and we can start to extrapolate and say, okay, how many of those vehicles will be strictly L4 vehicles, these self-driving taxis? And we can start to apply how long we think these taxis will last and get decommissions. How many of these taxis will need to be taken out every year and need to be replaced? And once we do that, we can start to say, okay, how is the market changing? How many vehicles are being added to this market every year that need to be produced? And we can start to add those back in, because now we have to account for vehicles that were previously decommissioned that weren't a part of L4 demand. And once we combine all these together, we get vehicle production. How many vehicles will need to be produced to sustain this market? And so here's the dashboard I have. We have our conservative, moderate, and progressive estimates, and we apply a logistic curve to our mobility as a service demand, and it's driven by these three variables right here. Our market limit, how many millions of vehicles, this is all in millions of vehicles, how many millions of vehicles we believe by the end of our model estimate will be in this market. A constant, because we actually have a value that we estimate that isn't changed by this spinner. And so we include this constant term for you to smooth it out a little bit and just kind of make the forecast make sense. And growth, how soon we believe we'll reach that limit. And we can start to look at, we apply another logistic curve at robotaxi demand. How much of this mobility as a service demand will be dedicated, will be these L4 taxis, these self-driving taxis. And mobility as a service being light vehicles used for light transportation that aren't owned for personal use, right? A car you own isn't mobility as a service, but a taxi or a rental car is. You're kind of renting that out for transportation purposes. And it's driven by, this robotaxi demand is driven by the same variables, but you can notice how changes made to this limit start to affect changes to the limit over here in robotaxi demand, because we believe that robotaxi demand is a function of mobility as a service demand. And this spinner changes it by 5% increments. You may say that, okay, I believe only 35% of this limit will actually be 35% of all mobility as a service will be L4 taxis. And you can push this curve out, pull it in, you might say it might get introduced faster, and you can say you have growth. You can change the acceptance, the adoption rate. And let's say you kind of screw everything up and you have this really wonky looking forecast and you don't really know how you got there. And I've included this macro here to reset all settings back to the default variables that I put in. And we estimate this range by using a Monte Carlo simulation that I've hidden. Let's see. I've hidden it from everyone, so they can't really see what's going on here. It's all the way back here. But estimate anywhere for our conservative 500 to 250,000 vehicles. And we apply just our Monte Carlo ideas to it, or standard deviations left and right. And that's how we get those market estimates, those market limits back there. When we get to annual robotaxi production, we can see that it's not actually driven on this sheet. We have to go to decommissions for that. And this is what pretty much drives the entire spreadsheet. Up here we have just kind of vehicle generation. We believe that these vehicles will improve in technology over time. They'll become more robust. So that's displayed by this mean life. It increases by half a year every generation. That's just kind of a yes/no type of answer we have. Just, yeah, put it in there. It seems to make sense. And this is the number of years after a vehicle is produced. And this is how many of those vehicles after that, at that year, will be decommissioned. So cumulatively, 3 years after a batch of vehicles will be produced, about 18% of them will be completely removed from the market. They'll need to be replaced. And then by year 4, what we have here is 81%, or about 82% of all vehicles that were produced in that initial year will be replaced. And this is the logistic curve again. It's driven by that mean life and the year, and a constant in here that you cannot change. But we apply that analysis for every single generation, and we can start to say we have a changing life cycle and a constant life cycle, and we'll get back to that in a minute. But here's pretty much the engine of the spreadsheet. Here's what's going on. We have that robotaxi demand that's driven from the market view spreadsheet and changes the market, but we'll get back to this. Well, actually we can do it now. So decommissions is a function of this changes in market, right? And changes in market is the number of vehicles, the change in demand, how many additional vehicles will need to be introduced to that market to satisfy demand, and the number of vehicles from the previous year that were decommissioned. And how this works is we use this VLOOKUP table up here to start to get that respective value for how many vehicles will need to be decommissioned that year. And we do that for every single year, and we sum them together. By the end of 2016, 0 vehicles will be decommissioned because there are 0 vehicles that have been produced. But if we start to go out, we have to account for other vehicles. What happens here is by the end of 2029, all the vehicles that were produced in 2029, by that first year, that many will be decommissioned. But we also have to account for the vehicles produced in 2028. So 2 years back, by the end of the second year, that many vehicles will be decommissioned, and so on and so forth. And we make the assumption that no vehicle will last beyond 12 years. And you have to do that for every single vehicle. And once we do that, we can start to get annual production, which is the change in robotaxi demand plus the decommissions of that year. And now we can start to look at, okay, this is a graph showing you the market limit, how much of that L4 demand, how much mobility as a service demand there is, and how much of that mobility as a service is the L4 demand. And we can see that there will remain non-autonomous options that L4 taxis just can't fill. Here you also look at annual production, cumulative production, long-run production, and these huge divots are results of the decommission cycle, right? These vehicles becoming much more robust, and we're expecting more vehicles to be produced, but all of a sudden we don't. These vehicles last longer, and they don't need to be replaced at the same rate, and we start to see things change. And the automotive industry is going to have to try and figure out how to prevent these dips. And that's where this changing and constant life cycle comes from. If we want to look at constant life cycle, okay, how many of these vehicles will be decommissioned? We expect it to follow about this logistic curve trend. This is what we believe. And then total long run production. And here's the city's data that I have. This is the data I was using to kind of estimate. I've done another regression analysis to kind of estimate the taxi market that isn't done in this paper. That's done elsewhere. But this is how I get the conservative taxi estimate. It's this huge nested if statement that I used before I knew about VLOOKUP tables. It's got vehicle population, everything here. Here's all the data that I used to drive my spreadsheet. And then here's that graph that I was showing to you earlier in the here's the graph of the number of vehicles that I estimated, right? New York City, LA, Chicago, and Houston are the largest markets, whereas Sacramento, New Orleans, there's really not much variation among these cities. But we kind of expect that. The states get homogenous after a while. Cities as well. And that is my L4 taxi presentation.